Hello there. Welcome to the Dozing Explorer.
I'm so glad you have found your way here to this quiet place of rest.
I am here to be your gentle guide to help you leave the day behind and drift into a place of calm and wonder. There is nothing you need to do, nothing to learn or remember. Your only task is to listen, to breathe, and to allow your mind to float on the sound of my voice. Tonight, our journey will be one of warmth and light. We are going to drift toward the very heart of our solar system, the source of all our light, all our warmth, all our life. We are going to explore our sun, but this is not a lesson. We will not be studying its complex physics. Instead, we will simply wander through its vast and golden mysteries. We will think of it as a colossal, gentle engine, a steady, pulsing heart that has warmed our small, blue world for billions of years. It is the silent, constant presence in our sky, the star that makes our world possible, a shimmering, golden sphere of unimaginable scale and power. This journey is a passive one, a collection of quiet wonders designed to give your mind a gentle place to rest. It is a soft, cognitive cushion, something to hold your attention just enough to keep it from wandering into the worries of the day, and to instead guide you softly toward the shores of sleep. And just before we begin our drift, if you find that these quiet explorations help you unwind and find peace, please consider subscribing to the channel. It is a simple, silent way to help other sleepy souls find their way to this restful harbor. But for now, all of that is far away. There is nothing left for you to do today. You have done enough. You can let go of all your thoughts, all your plans, all your concerns. Let them dissolve like clouds in the vast, clear sky. Feel the weight of your body settling in, growing heavy, feeling supported and safe. Give yourself permission to let go, settle in, breathe deeply, and let our gentle journey to the sun begin. Our sun is a star of almost unimaginable size, a colossal sphere of glowing gas that truly dwarfs our world. If you were to imagine the sun as a hollow ball, you could fit 1 million planets the size of Earth inside of it. It is so vast that its surface, which we see as a smooth golden disk, is a roiling, bubbling ocean of plasma with currents and waves larger than entire continents. This single star, our star, accounts for more than 99% of all the mass in our entire solar system.
Everything else, all the planets, moons and asteroids, are just the tiny,
leftover specks of dust from its creation. The light that you see from the sun, the warmth you feel on your skin, begins its journey in the most extreme place in the solar system, the sun's core. The core is a place of such immense pressure and heat that it is difficult to comprehend. The temperature there reaches over 15 million degrees Celsius, or 27 million degrees Fahrenheit. It is so hot and so dense that the very atoms of hydrogen are crushed together, fusing to become helium. This process, nuclear fusion, is the sun's engine. It is a continuous, controlled explosion that has been burning steadily for more than 4.5 billion years, releasing a torrent of pure energy in the form of light. When that energy is born in the sun's core, it does not travel straight out. It begins an incredibly long and slow journey, a journey that can take over 100,000 years. The energy in the form of a photon of light is created, but it almost immediately collides with a dense particle of matter. It is absorbed and then re-emitted in a random direction. It takes another tiny step and collides again. It is a slow, chaotic dance, a random walk, as the light zigzags its way through the sun's incredibly dense interior, bouncing from atom to atom for an age before it finally reaches the surface and is free to travel. After its long, 100,000-year journey to escape the sun's interior, that same photon of light is finally released from the surface. From that moment, its journey to us is a pure, uninterrupted sprint across the void of space. It travels at the fastest speed possible, the speed of light, covering 186,000 miles every single second. The 93 million mile gap between the Sun and our world is crossed in just over 8 minutes. This means the sunlight that warms your face on a bright afternoon is ancient. It was born in the Sun's core before human civilization began, and it then spent its last 8 minutes crossing the vastness of space just to end its long journey here. The Sun does not burn in the way a fire on Earth does. A fire is a chemical reaction where a substance combines with oxygen. If the Sun were made of coal, it would have burned itself out in just a few thousand years. The Sun's power is nuclear. Its fuel is hydrogen, the simplest and most abundant element in the universe. The Sun's core is a massive nuclear reactor, but instead of splitting atoms apart, it fuses them together. It takes 4 hydrogen atoms and, under the immense pressure, squeezes them into one new helium atom. In this process, a tiny amount of the mass is not needed, and it is converted directly into a pure, colossal burst of energy. As described by Einstein's famous equation, e⁻²⁶ as the Sun is not a solid object. It is a roiling ball of plasma, and because it is not solid, it does not rotate as a single, solid piece like the Earth. Instead, it spins at different speeds. The Sun's equator, its middle, spins quite fast, completing a full rotation in about 25 Earth days. But its poles, the very top and bottom of the Sun, spin much more slowly, taking around 35 days to complete one turn. This strange differential rotation, with the middle spinning faster than the top, is what stretches and twists the Sun's powerful magnetic fields,
tangling them up like elastic bands until they eventually snap,
creating the dramatic events we see as sunspots and solar flares. The dark patches we sometimes see on the Sun's surface are called sunspots. They are not actually dark, but are cool spots on the Sun's intensely hot surface. A sunspot is a temporary patch on the Sun that is cooler than the area surrounding it, which is why it appears dark in comparison. These spots are the size of planets, and they are created by intense, localized magnetic fields. These magnetic fields become so strong that they push back against the hot gas rising from below, blocking the heat and allowing that small patch of the surface to cool down from a blistering 6,000 degrees to a slightly more placid 4,000 degrees. Our Sun is not a silent, steady ball of light. It is a dynamic, active star with its own form of weather. Sometimes the tangled magnetic fields near a sunspot will suddenly snap and reconnect, releasing a tremendous, sudden burst of energy and light. This is called a solar flare. A single solar flare can release the energy equivalent of billions of nuclear bombs exploding all at once.
It is a colossal flash of light, a burst of radiation that travels out through the solar system at the speed of light.
One of the most powerful and energetic events in our entire solar system, sometimes, a solar flare is accompanied by an even larger event, a coronal mass ejection, or CME. This is not just a flash of light, but a physical explosion of the Sun's own substance. An immense bubble of magnetized plasma, billions of tons of the Sun's outer atmosphere, is blasted away from the Sun, traveling out into space at speeds of over 1 million miles per hour. This vast cloud of solar material journeys through the solar system, and if it happens to be aimed at Earth, it can interact with our planet's own magnetic field, triggering the beautiful, shimmering lights of the aurora. The Sun is constantly breathing a gentle, invisible wind out into space.
This is the solar wind.
It is not like wind on Earth, but is instead a continuous stream of tiny, charged particles, mostly electrons and protons, that are boiling off the Sun's incredibly hot outer atmosphere, the corona. This wind flows outward in all directions, traveling at 1 million miles an hour, and it flows past every planet in our solar system. It is this solar wind that creates the beautiful, long tails of comets as it pushes the comet's dust and gas away from the sun. Our own planet is protected from this constant wind by our magnetic field, which deflects the particles safely around us. The Earth is protected by an invisible shield, a bubble called the magnetosphere, which is generated by the molten iron core of our planet. When the solar wind or a giant coronal mass ejection flows from the sun, it first encounters this magnetic shield. Most of the particles are deflected, flowing around our planet like water around a stone in a stream. But some of these solar particles are captured. They are funneled down along the magnetic field lines toward the north and south poles. As they speed into our upper atmosphere, they collide with atoms of oxygen and nitrogen, causing them to glow. This beautiful, shimmering collision is what we see as the aurora, the northern and southern lights. 12. The sun is not yellow or orange, as we often see it in pictures. The true combined color of the sun is actually white. It emits light across the entire visible spectrum, and if you were in space, it would appear as a brilliant, pure white disk. The reason it appears yellow or red to us on Earth is because of our planet's atmosphere. As the white sunlight streams through the air, the shorter wavelengths of light, the blues and the violets, are scattered away by the air molecules.
This is why the sky looks blue.
What's left over for our eyes to see is the warmer end of the spectrum, the yellows, oranges and reds, which become especially beautiful during a sunrise or sunset when the light has to pass through even more air. So the sun's outermost atmosphere, the corona, is one of its greatest mysteries. This faint, wispy halo of plasma stretches millions of miles out into space, and it is only visible from Earth during the fleeting, magical moments of a total solar eclipse. The mystery is its temperature. The surface of the sun, the photosphere, is about 6,000 degrees Celsius. But the corona, which is outside the surface, is somehow, bafflingly, hundreds of times hotter, reaching temperatures of over 1,000,000 degrees. How the sun heats this outer layer to such an extreme temperature, hotter than its own surface, is a profound puzzle that scientists are still working to solve. But we often think of the sun as a medium-sized star, but this is a bit misleading. It is true that there are massive, giant stars out there that are hundreds of times larger. But when we look at the entire population of stars in our Milky Way galaxy, our sun is actually brighter and more massive than about 90% of them. The most common type of star is a small, cool, dim red dwarf. Our sun, a G-type main sequence star, is a relatively large, bright, and stable member of the galactic community, a calm and steady presence that has allowed life on our planet the long, uninterrupted time it needed to evolve. Our sun is not alone in its journey through the galaxy. The entire solar system, including the sun, our Earth, and all the other planets, is moving at an incredible speed. We are traveling through the Milky Way galaxy at an average speed of about 450,000 miles per hour. Even at this breathtaking pace, our galaxy is so colossally large that it takes our solar system over 230 million years to complete one single orbit around the galactic center. This means that the last time our solar system was in this same part of the galaxy, the first dinosaurs were just beginning to walk the Earth. See, the sun's energy is what powers nearly all life on our planet. This process, photosynthesis, is a quiet everyday miracle. Plants, algae, and some bacteria have the amazing ability to take the simple, raw ingredients of carbon dioxide from the air and water from the soil, and use the energy from pure sunlight to turn them into sugars and food. This process not only creates the food that forms the basis of almost every food chain on Earth, but it also releases the oxygen that we, and most other animals, need to breathe. Every breath you take is a gift from the sun, captured and released by a simple green leaf. So the sun's immense gravity is what holds our entire solar system together. It is a constant, invisible anchor. The Earth is traveling through space at over 67,000 miles per hour. We are in a constant state of falling toward the sun, but because we are also moving so fast sideways, we constantly miss it. This perfect balance between our forward speed and the sun's gravitational pull is what we call an orbit. It is a stable, continuous fall that has kept our planet locked in a gentle, predictable path for billions of years, giving us the steady, reliable cycle of the season. The sun is made almost entirely of the two simplest elements. If you could take a sample of the sun, you would find that it is about 74% hydrogen and 24% helium by mass. All the other elements, the metals we know like oxygen, carbon, iron, and neon, make up less than 2% of the sun's total mass. Our own planet, however, is made almost entirely of these heavier elements. This tells us a beautiful story of our origins. It means that our sun is a second-generation star. The heavy elements that form our planet and that form us were not made in our sun. They were forged in the fiery heart of a different, much larger star, which lived and died in a massive supernova explosion billions of years ago, scattering its ashes across space to form our solar system. The surface of the sun, the photosphere, is not a smooth, calm sea of light. It is a bubbling, churning, and incredibly detailed landscape. If you could look at it up close, you would see it is covered in a pattern of granules. Each granule is a cell of hot, rising plasma about the size of the state of Texas. Hot gas rises in the center of the granule,
Spreads out, cools,
and then sinks back down along the darker, cooler edges. This constant roiling motion is called convection. It is the same process as water bubbling in a pot, but on a vast solar scale. Each granule only lasts for about 10 or 15 minutes before it dissolves and is replaced by a new one, part of the endless churning engine of the sun's surface. Our sun is a star in the quiet, stable main sequence phase of its life. This is the long adult phase for a star, where it steadily fuses hydrogen into helium in its core. Our sun has been in this phase for about 4.6 billion years, and it is about halfway through its supply of hydrogen fuel. It is so massive that it has enough fuel to continue burning just as it is, steadily and calmly, for another 5 billion years. This incredible long-term stability is one of the key reasons that complex life had the time to evolve on Earth, protected by a star that has not changed in any significant way for all of our planet's history. And the sun is so massive that its gravity, its pull, extends for an incredible distance. The edge of our solar system is not at the orbit of Neptune or even Pluto. The sun's gravitational influence extends out for more than a light year to a vast theoretical sphere of icy bodies called the Oort cloud. This is a cold, dark realm where billions or even trillions of comets are thought to be slowly orbiting our distant sun. This cloud is the faint, final boundary of the sun's kingdom, a remnant from the formation of the solar system, held in place by the same gentle, constant gravity that holds our own world. The sun makes a sound, but it is not a sound we could ever hear. The sun's entire body is constantly vibrating like a colossal cosmic bell. The roiling, convective motions deep inside the sun create immense sound waves, pressure waves that bounce from one side of the sun to the other and back again. These vibrations cause the surface of the sun to gently and rhythmically rise and fall, in some places by several miles, in a complex resonant pattern. Scientists can study these vibrations in a field called helioseismology to see deep inside the sun, using sound waves to map its hidden inner structure, just as earthquakes reveal the structure of the Earth's core. The sun's energy, when it reaches our planet, is responsible for our weather. The sun does not heat the Earth evenly. It shines more directly on the equator and at a glancing angle on the poles. This difference in heating creates vast temperature imbalances. The warm tropical air rises and moves toward the poles, while the cold polar air sinks and moves toward the equator. This vast global circulation of heat, all powered by the sun, is what creates our prevailing winds, our ocean currents, and the high and low pressure systems that give us clouds, rain, and all the weather we experience every day. The sun will not last forever. In about 5 billion years, it will finally run out of the hydrogen fuel in its core. When this happens, the sun's life as a stable star will end, and it will begin to die. The core, no longer supported by the outward pressure of fusion, will begin to collapse under its own gravity. This collapse will heat the core to an even more extreme temperature, so hot that it will ignite the hydrogen in a shell surrounding the core. This new, frantic burning will be so intense that it will cause the sun's outer layers to expand and expand and expand, beginning its new life as a red giant. So when our sun becomes a red giant, it will grow to a truly monstrous size. Its expanding outer layers will swell to become hundreds of times larger than they are today. The sun will grow so large that it will swallow the innermost planets, Mercury and Venus. It may even expand far enough to swallow the Earth itself. The surface of this new giant star will be cooler, giving it a deep reddish-orange color. It will be a vast, luminous and terrifyingly large star, a final dramatic phase of its life, its expanding, dying breath filling the inner solar system. 26. After its brief and dramatic life as a red giant, the sun's core will have one final burst of activity. It will become hot enough to fuse helium, the ash of its previous life, into heavier elements like carbon and oxygen. But this fuel will not last long. Eventually, this fusion will also stop and the sun's engine will turn off for good. Without the outward pressure of fusion, the sun's outer layers will drift away from the core, expanding out into space as a beautiful, glowing, smoke ring-like structure known as a planetary nebula. This colorful, ghostly cloud will be the sun's final gift, its substance expanding back into the galaxy. At the center of that beautiful, expanding cloud of gas, the sun's old core will be left behind. This remnant, this ember, is called a white dwarf. It will be an object of incredible density. The entire remaining mass of the sun, about as much as it has now, will be crushed down into a sphere only the size of the planet Earth. A single teaspoon of this white dwarf material would weigh as much as a truck. This star will no longer be generating any new heat. It will be just a hot, dense, slowly cooling ember, shining with a faint, white light, and it will spend the next trillions of years slowly fading, like a dying campfire until it becomes a cold, dark, black dwarf in the endless night of space. Above the sun's visible surface, the photosphere, is another layer called the chromosphere, or the sphere of color. This is a thin, reddish layer of gas that is only visible for a few fleeting seconds during a total solar eclipse, at the moment just before or just after the moon has completely blocked the sun. This layer is a forest of giant, fiery spires of plasma called spicules. These spicules are jets of hot gas as tall as mountains that are constantly shooting up from the surface at thousands of miles per hour, rising and falling in a matter of minutes, a dynamic, fiery grass that covers the entire sun. The sun's powerful magnetic field extends far beyond its surface. It fills the entire solar system in a complex, spiraling structure known as the interplanetary magnetic field. Because the sun is rotating, it twists this magnetic field into a giant pinwheel shape called the Parker spiral. As the solar wind flows out from the sun, it is forced to travel along these spiral magnetic field lines. This means that by the time the field reaches Earth, it is not pointing straight from the sun, but is angled, like the water from a spinning lawn sprinkler, a vast, invisible, rotating magnetic structure that we are all passing through. So, the sun not only emits light we can see, but it also shines brightly in forms of light that are invisible to our eyes. It is a powerful source of ultraviolet or UV light. It is this high-energy light that causes sunburns and, over long periods, can be harmful to life. But our planet has a natural protective sunscreen. High in our atmosphere, a layer of oxygen molecules absorbs the most energetic UV light. And in the process, these molecules are transformed into a new molecule, ozone. This ozone layer then becomes a powerful shield, absorbing almost all of the most dangerous UV rays, protecting life on the surface below. The sun, like many stars, is a variable star, but only slightly. Its total energy output is not perfectly constant. It goes through a gentle, predictable solar cycle that lasts about 11 years. Over this 11-year period, the sun's activity will rise from a quiet minimum with very few sunspots to a turbulent solar maximum, where its surface is covered in many large sunspot groups, and it erupts with frequent, powerful solar flares. This cycle is driven by the slow tangling and resetting of the sun's global magnetic field. It is a slow, steady heartbeat, a rhythm of activity that has been observed and recorded for centuries. During a solar maximum, when the sun is most active, its X-ray and ultraviolet light output can increase significantly. This extra energy floods into Earth's upper atmosphere, heating it and causing it to expand or puff up like a marshmallow. This can cause problems for satellites in low Earth orbit. As the atmosphere expands, it creates more atmospheric drag on these satellites, slowing them down in their orbits. If this drag is not corrected for, the satellites can slowly spiral downward, their orbits decaying, all because of the sun's distant, invisible, and turbulent activity. For all of history, the sun was a complete mystery. The ancient Greeks believed it was a golden chariot driven across the sky. It was not until the 1920s that we truly began to understand it. A young astronomer named Cecilia Payne-Gaposchkin, in her PhD thesis, was the first to propose that the sun was made overwhelmingly of hydrogen and helium. At the time, this was a radical idea. Scientists believed the sun was made of the same heavy elements as the Earth. Her discovery, which was initially dismissed, fundamentally changed our understanding of the universe, proving that the stars are not like the Earth, but are an entirely different class of object, vast, simple, and ancient. The sun is so large and its gravity so strong that it actually bends the fabric of space-time around it, like a heavy bowling ball sitting on a trampoline. The planets, including Earth, are not being pulled by a long, invisible rope. They are simply following the curves, the warps in space-time that are created by the sun's immense mass. In 1919, during a solar eclipse, astronomers observed the light from distant stars passing near the sun. They saw that the starlight was indeed bent, just as Einstein's new theory of general relativity had predicted. It was the first profound proof that gravity is not a force, but a curvature of the universe itself. So we are all, in a very real sense, children of the stardust. The heavy elements that make up our world, the carbon in our bodies, the oxygen we breathe, the iron in our blood, the silicon in the rocks, were not created in our sun. Our sun is not massive enough to forge these elements. They were created in the hearts of much larger, more massive stars that lived and died billions of years ago. These giant stars ended their lives in colossal supernova explosions, scattering these newly created heavy elements across the galaxy. This stardust then mixed with clouds of hydrogen and helium, which eventually collapsed to form our solar system, our sun,
and our Earth. We are made from the ashes of long-dead stars, and the sun's energy can be captured directly.
A solar panel, a photovoltaic cell, is a remarkable invention. It is made of special materials, usually silicon, that have a unique property. When a photon of sunlight, a tiny particle of light, strikes the panel, it can knock an electron loose from its atom. The panel is designed to capture this freed electron and guide it into a circuit, creating a flow of electricity. It is a quiet, clean, and direct transformation. It is the long 100,000-year journey of a photon from the sun's core, ending its 8-minute trip to Earth by being converted in an instant into the energy that can power a light in your home. The sheer amount of energy the sun produces is staggering. Every single second, the sun's core fuses about 600 million tons of hydrogen into 596 million tons of helium. That missing 4 million tons of mass is converted directly into pure energy. This is the energy that lights up the entire solar system.
Of that colossal, unimaginable torrent of power, only a tiny
fraction, less than 1/billionth of 1%, actually strikes the planet Earth. All the sunlight, all the warmth, all the energy that powers our entire planet, our weather, and our lives is just the faintest, most minuscule splash from the sun's constant. Radiant output, 38, if the sun's core, its fusion engine, were to suddenly and magically turn off right this second, we would not know it for a very long time. We would continue to see its light and feel its warmth, as if nothing had changed. This is because the light that is shining now was created, on average, over 100,000 years ago, and it is still in the middle of its long, random walk to get to the surface. It would take tens of thousands or even hundreds of thousands of years for the last of the light to make its way out, and for the sun to slowly, gradually begin to grow dim. It is a star with a profound built-in lag time due to its own immense density. The sun's magnetic field is incredibly powerful and complex. We see its effects as sunspots, which are areas where the magnetic field is about 1,000 times stronger than the field at Earth's surface. But there are also vast, graceful loops of plasma that follow the sun's magnetic field lines, arcing up from the surface and back down again. These are called solar prominences. They can be hundreds of thousands of miles long, large enough for the Earth to pass through. They can hang in the sun's atmosphere for days or weeks, like fiery, glowing bridges held in place by the invisible, powerful magnetism of the sun. 40. Sometimes a solar prominence can become unstable and erupt, breaking free from the sun's gravity and magnetic field. This is a prominence eruption, and it is one of the most graceful and beautiful sights in the solar system. An immense, twisted rope of hot gas, larger than a dozen planets, will slowly rise from the sun and blast out into space, untethering itself and floating away into the solar wind. It is a quiet, slow-motion explosion, a release of a truly colossal amount of solar material, all driven by the slow, steady tangling and snapping of the sun's magnetic fields. See, for centuries, people have tried to link the sun's 11-year sunspot cycle to events on Earth, such as stock market changes or major weather patterns. While most of these connections are not real, there is one historical mystery that may be real. Between the years 1645 and 1715, there was a period of time, now called the Maunder minimum, where astronomers observed almost zero sunspots. The sun's cycles seemed to have turned off. This period of solar quiet coincided perfectly with the Little Ice Age in Europe, a time of bitterly cold winters. It is a tantalizing clue that the sun's slight variability may have a much more significant and direct impact on our climate than we realize. Had the sun not only produces the solar wind, it also is responsible for cosmic rays. While most cosmic rays are high-energy particles from distant supernovas, our sun also produces its own lower-energy versions. During a powerful solar flare, the sun can accelerate protons and other particles to near the speed of light. These solar cosmic rays stream out and can be dangerous to astronauts in space who are outside the protection of Earth's atmosphere and magnetic field. These particles can pass through the walls of a spacecraft and are one of the primary health concerns for any long-term mission to the Moon or Mars. The color of the aurora, the northern lights, tells us a beautiful story about our own atmosphere. When the solar particles stream down and strike the air, the color they produce depends on which atom they hit and how high up it is. The most common color, a beautiful shimmering pale green, is the color of oxygen atoms being struck at an altitude of about 60 to 150 miles. Sometimes at the very top of the aurora, you can see a faint, deep red. This is also oxygen, but in the very thin, high-altitude air, where the atoms have more time to glow. The blues and purples, often seen at the bottom of the auroral curtains, are the light from nitrogen atoms glowing in the lower, denser parts of the atmosphere. The sun's light exerts a tiny, but measurable physical pressure. Light is made of photons, and while they have no mass, they have momentum. When a photon strikes an object, it gives it a tiny push. This radiation pressure is minuscule, but over millions of years it can have real effects. It is this pressure that is thought to clean out the very smallest microscopic dust particles from the inner solar system, pushing them slowly away from the sun. It is also the principle behind a solar sail, a futuristic concept for a spacecraft. Such a craft would unfurl a vast, thin, mirror-like sail and be pushed through space, slowly but constantly, by the gentle, continuous pressure of sunlight itself. The sun is not a perfect sphere, because it is a rotating ball of gas, and not a solid. It bulges slightly at its equator. The sun's equatorial diameter is about 6 miles wider than its polar diameter. This is a tiny, almost imperceptible difference for an object that is nearly 1 million miles across. It is so close to being a perfect sphere that if you were to shrink it down to the size of a billiard ball, it would be one of the most perfectly round objects ever made, far smoother and more spherical than any man-made ball. It is a testament to the immense, crushing, and perfectly symmetrical force of its own gravity. And for all of its power, the sun is an incredibly inefficient engine, which is a good thing for us. The power is generated only in its tiny, dense core. The amount of power produced per cubic meter in that core is actually less than the energy generated by a common, decaying compost pile. The sun is not hot because its reactions are powerful in a small space, but because it is so enormous. It is a vast, colossal, and incredibly well-insulated sphere. And this tiny, gentle, compost heap level of energy, generated over a region the size of 100 planets, is trapped inside, building up to the millions of degrees that we see, and allowing its fuel to last for billions of years. When the sun becomes a white dwarf, it will be made of a new, exotic form of matter. The gravity is so strong that it crushes the atoms themselves, forcing the electrons out of their orbits and creating a degenerate electron gas. The star is no longer held up by heat pressure, but by a quantum mechanical rule that states that no two electrons can be in the same place at the same time. They push back, creating a new, powerful degeneracy pressure that holds the star up against gravity. It is a star held up not by motion and heat, but by a fundamental quantum law, a truly strange and stable state of matter. The beautiful planetary nebula that the sun will create when it dies is one of the most fleeting objects in the cosmos. The colorful glowing gas clouds that we see and photograph are expanding rapidly. They only glow because the hot, white dwarf at their center is bathing them in intense ultraviolet light, causing the gas to fluoresce like a neon sign. This phase only lasts for about 10 or 20,000 years. After that, the central star will have cooled too much to light up the gas, and the gas itself will have expanded so far that it becomes too thin to see. It is a brief, final and beautiful goodbye from a dying star. The solar wind and the interplanetary magnetic field it carries create a vast protective bubble around our entire solar system. This bubble is called the heliosphere. It is the region of space where the sun's influence, its wind, is dominant. This bubble acts as a shield, protecting the inner solar system from the high-energy interstellar cosmic rays that are flying through our galaxy. The heliosphere pushes back against this interstellar wind, creating a boundary, a shock, where the two winds meet. This is the true outer edge of our solar system, the frontier, where the sun's breath finally gives way to the vast, open galaxy beyond. Source, the sun. Our sun is a constant, steady, and reliable presence in our lives. It has risen and set every single day of human history. Its energy has powered our planet, grown our food, and warmed our skin. It is the anchor of our world and the engine of our lives. It is a star, just one of hundreds of billions in our galaxy, but it is our star. It is a profound, everyday reminder of our connection to the cosmos. The light it provides is an ancient echo of its deep, nuclear heart, a heart that has been beating for billions of years and will continue to beat for billions more, a silent, golden guardian in our sky. The photosphere, which we call the sun's surface, is not a solid surface at all. It is a layer of gas about 300 miles thick that marks the point where the sun's plasma becomes opaque. Below this layer, the gas is so dense that light is trapped, endlessly bouncing and scattering. But in the photosphere, the gas finally becomes thin enough that photons of light can escape and travel freely into space. When we look at the sun, we are not seeing a thing, but an edge. We are seeing the exact altitude where the sun becomes transparent, the glowing, visible boundary between the sun's dense interior and the blackness of space. So the sun's magnetic field, the one that drives its 11-year cycle, actually flips its polarity at the peak of each solar maximum. The sun's north magnetic pole becomes its south magnetic pole, and the south pole becomes the north. This happens as the old magnetic field, tangled and chaotic, fades away, and a new magnetic field, with the opposite orientation, rises up to take its place. This colossal polar flip is the resetting mechanism for the entire solar cycle. It is a slow, gradual process taking several months, but it marks the high point of the sun's activity, after which the sun slowly begins to quiet down toward its next minimum, before the cycle begins all over again. The energy from the sun is the ultimate source of almost all the energy we use on Earth. The sunlight that grew ancient forests
millions of years ago was captured and stored as chemical energy in those plants.
Over geological time, those plants were buried, compressed, and transformed into the coal, oil, and natural gas that we call fossil fuels. When we burn these fuels, we are releasing ancient trapped sunlight, solar energy from a long-vanished, prehistoric world to power our modern one. It is a vast planetary-scale battery charged by the sun over hundreds of millions of years. 54, the sun's light is not the only thing it sends us. It is also the source of a constant ghost-like stream of particles called neutrinos. These tiny, nearly massless particles are created in the nuclear fusion reactions deep in the sun's core. Unlike a photon of light, a neutrino does not interact with matter. The moment it is born, it flies straight out of the sun's core, passing through the entire dense star as if it were empty space, and reaches Earth just 8 minutes later. Right now, as you are lying here, hundreds of trillions of these solar neutrinos are passing through your body. Every single second, a harmless, invisible, and direct messenger from the sun's fiery heart. For decades, the sun's neutrinos were a profound puzzle. Our detectors on Earth built deep underground in vast mines to shield them from all other radiation, were only catching about 1/3 of the neutrinos that our theories predicted the sun should be making. This solar neutrino problem was a crisis. Did we not understand the sun, or did we not understand the neutrino? The answer, it turned in, was the neutrino. We discovered that neutrinos can oscillate, or change their flavor, during their 8-minute journey from the sun. They were not missing. They were simply changing their identity, arriving at Earth as a different type of neutrino that our original detectors could not see, a truly strange and wonderful quantum mystery. And when the sun was very young, just after it formed from its collapsing cloud of gas and dust, it was a much more violent and active star. It was a T-Tauri star, a turbulent adolescent star. During this phase, it would have had a much stronger and more chaotic magnetic field, producing superflares thousands of times more powerful than the ones we see today. It also would have been spinning much faster. But over its first 100 million years, its powerful solar wind acted as a brake. By constantly flinging particles out into space, the sun slowly spun down, its rotation slowing, and it settled into the calm, stable, and predictable star that we know today, a crucial step that allowed its young planets, like Earth, to become more habitable. The sun's gravity is so immense that it can capture objects from interstellar space. In 2017, astronomers detected the first ever known interstellar visitor, an object they named Oumuamua. It was a small, rocky, cigar-shaped object that had been wandering through the vast, empty space between the stars for millions or perhaps billions of years. It was not in orbit. It was just passing through. It fell toward our sun, was whipped around by the sun's powerful gravity, and then flung back out, continuing its endless journey into the dark. It was a brief chance encounter, a reminder that our solar system is not isolated, but is a small island in the vast open ocean of the galaxy. The study of helioseismology is how we know what the inside of the sun looks like. Just as seismologists use earthquakes to map the interior of the Earth, solar astronomers watch the sunquakes on the sun's surface. These are the vast rhythmic vibrations, the sound waves that are echoing through the entire star. By measuring the ripples these sound waves make on the surface, scientists can build a detailed 3D map of the sun's hidden interior. This is how we know with such confidence the size of the sun's core, the depth of its convection zone, and even how the plasma is flowing. Deep beneath the visible surface we can see. The sun's energy is not just light and heat, it is also the engine of the water cycle on our planet. The sun's warmth beats down on the oceans, lakes, and rivers, giving the water molecules energy. This energy allows them to evaporate, to break free from the liquid, and rise into the atmosphere as an invisible gas, water vapor. As this warm, moist air rises, it cools. The water vapor condenses back into tiny liquid droplets, forming the clouds we see in the sky. When these droplets become heavy enough, they fall as rain or snow, returning the water to the surface, where the entire gentle, sun-powered cycle begins all over again. The sun's core, where fusion happens, is only about 25% of the sun's total radius, but it contains almost half of the sun's entire mass. It is a region of truly unimaginable density. The plasma there is crushed by gravity to a density over 150 times greater than that of water and 10 times denser than solid lead. Yet it is not a solid. It is a plasma, a unique state of matter where it is so hot that the electrons have been stripped from their atoms, creating a seething, superheated soup of free-floating protons and electrons, a perfect, dense, and fiery environment for the nuclear fusion that powers our world. Outside the sun's core is a vast, silent layer known as the radiative zone. This layer makes up the bulk of the sun's interior. In this zone, the plasma is still incredibly hot and dense, but it is not hot or dense enough for fusion to occur. Here, energy is transported not by physical motion, but by light. This is the region where that 100,000-year random walk happens. A photon is created, it travels a fraction of a millimeter, and it is absorbed. It is then re-emitted and it travels another tiny step. It is a staggeringly slow, dense, and patient transfer of energy as the light from the core diffuses outward like a drop of ink, slowly spreading through a vast, dense, and glowing ocean. The outermost layer of the Sun's interior is the convective zone. This zone begins about 70% of the way out from the center, and it is the last 30% of the Sun's radius. In this region, the plasma is cooler and less dense, and it begins to behave like boiling water. Here, energy is no longer transported by light, but by the physical churning motion of the gas itself. Vast continent-sized blobs of hot plasma are heated from below in the radiative zone. They become buoyant and rise to the surface where they release their heat, cool, and then sink back down again. This is the great bubbling pot that creates the granules we see on the Sun's surface. The Sun has a lifespan that is, in a way, determined by its size. Our Sun is a G-type star and will live for about 10 billion years in total. A star that is more massive, one that is 10 or 20 times the mass of our Sun, will have a much, much shorter life. Even though it has more fuel, its immense gravity creates so much pressure in its core that it burns through that fuel at a truly frantic, ferocious rate. A massive star may only live for a few million years, a mere cosmic eye blink, before it exhausts its fuel and explodes as a supernova. Our Sun's average size is what gives it its long, stable, and life-giving calm. A star that is less massive than our Sun, a small red dwarf, will have a lifespan that is almost difficult to imagine. These stars are small, cool, and dim. Their cores are much less pressurized, so they sip their hydrogen fuel at an incredibly slow rate. A red dwarf star can live for trillions of years, far, far longer than the current 13.8 billion year age of the entire universe. These tiny, faint, long-lived stars are the most common in the galaxy, and they will continue to glow with a dim red light like cosmic embers, long after our own Sun and every star like it has faded and died. The Sun is constantly evaporating. This is what the solar wind is. The Sun's gravity is immense, but its outer atmosphere, the corona, is so colossally hot at millions of degrees that the particles there are moving at incredible speeds. They are moving so fast that the Sun's gravity simply cannot hold on to all of them. The fastest moving particles are able to escape, boiling off the Sun's atmosphere and streaming out into space. This constant, steady evaporation is a tiny loss for the Sun, but it fills the entire solar system. Every second, the Sun loses about 1 million tons of its mass to this solar wind, a wind of its own, dissolving substance. If the solar cycle, with its 11-year rhythm, is a relatively new discovery, for most of human history, the Sun was seen as a symbol of perfection, a flawless, unchanging heavenly body. In the 1600s, astronomers like Galileo used the new invention, the telescope, to look at the Sun very carefully by projecting its image, and were shocked to discover that its perfect face was blotted with dark, irregular spots. This observation that the Sun was imperfect and changing was a profound and revolutionary moment in science. One of the first steps in demystifying the heavens and realizing that the Sun was not a magical orb, but a dynamic, physical, and active place. 81. The Sun's 11-year cycle is, more accurately, a 22-year magnetic cycle. It takes 11 years for the Sun to go from a quiet minimum to a solar maximum and back to a minimum. But at this new minimum, the Sun's magnetic north and south poles are flipped from where they were before. It takes another 11-year cycle for the Sun to go through another maximum and for its poles to flip again, returning them to their original starting position. So the full, complete solar cycle for its magnetic field to go from start to finish is actually 22 years long. 2. The most energetic solar flares are classified by a letter system: C, M and X. C flares are small and have few, if any, effects on Earth. M flares are medium-sized and can cause brief radio blackouts in our polar regions. But X flares are the monsters. They are the largest, most powerful explosions in the solar system. A powerful X flare can release a torrent of radiation that can cause planet-wide radio blackouts. And if it is aimed at Earth, it can trigger a geomagnetic storm so strong that it can overload power grids, damage satellites, and produce the auroras so powerfully that it can be seen as far south as Florida or Cuba. To the largest, most powerful solar storm ever recorded in human history was the Carrington event in 1859. A colossal solar flare and coronal mass ejection struck the Earth. At the time, the only high-tech equipment was the telegraph system. The storm was so powerful that it induced electrical currents in the telegraph wires, blowing out the system's shocking operators, and in some cases, causing the wires to spark and set fires. The aurora it produced was seen all over the world, so bright that people in the Rocky Mountains reported waking up in the middle of the night, thinking it was dawn. If a storm of that magnitude were to strike us today, it would be a true global catastrophe for our satellite and power grid-dependent civilization. The Sun's influence, its heliosphere, is not a perfect sphere. As the Sun and our solar system travel through the galaxy, we are moving through the thin interstellar medium. This creates a wind, just like the wind you feel on your face when you are moving. This interstellar wind pushes against our heliosphere, compressing it on the front side and stretching it out into a long, comet-like tail on the back side. Our solar system is not a bubble, but is more like a teardrop, a bubble with a long, flowing tail moving through the galaxy, a structure carved by our motion through the cosmic fog. When the Sun was very young, its intense ultraviolet and X-ray radiation was much stronger than it is today. This had a profound effect on the early solar system. This wind of high-energy light was so strong that it blasted away the atmospheres of the inner planets. It is believed that Earth, Venus, and Mars may have had thick, primary atmospheres of hydrogen and helium, which they captured from the original solar nebula. But the young, raging Sun stripped this first atmosphere away, and the atmospheres we have now are secondary atmospheres, which were created later, outgassed from volcanoes and delivered by comets.
After the Sun had settled down. The Sun is in a constant,
delicate gravitational dance with all of its planets. We often say that the planets orbit the Sun, but this is not strictly true. The planets, especially the massive ones like Jupiter, also pull on the Sun. This means that the Sun and Jupiter both orbit a common center of mass, a point in space called the barycenter. Because the Sun is so much more massive, this barycenter is very close to the Sun, but it is not at its exact center. This means that our Sun is not stationary. It is constantly wobbling in a small, complex, looping dance, as all of its planets, especially Jupiter, pull it this way and that. This wobble, this reflex motion of a star as it is pulled on by its orbiting planets is one of the main ways we find exoplanets, or planets orbiting other stars. We cannot see the planet itself, as it is too small and dim, hidden in the star's glare. But we can look at the star's light. By measuring the star's spectrum, we can see if it is wobbling back and forth, moving slightly toward us and then slightly away from us. This tiny rhythmic Doppler shift in the star's light is the unmistakable gravitational signature of an unseen, orbiting planet pulling its parent star in a cosmic, gravitational dance. Keat, the solar constant, is the name for the amount of energy from the Sun that strikes a square meter of Earth's upper atmosphere. It is, on average, about 1,361 watts of power. This is a tremendous, steady and reliable flow of energy. It is this number, this constant, that is the starting point for all of our climate models and for all of life. It is enough energy, in theory, to power more than a dozen bright, old-fashioned light bulbs for every single square meter of our planet that is facing the Sun. It is a constant, steady allowance of energy from our star, which powers our entire world. But the Sun's energy is what creates the fossil fuels on Earth, but it is also the source of renewable energy. The Sun's uneven heating of the Earth creates the wind, which we can capture with wind turbines. The Sun's power, driving the water cycle, lifts water up into the mountains, where it forms rivers that we can dam using gravity to spin turbines and create hydroelectric power. And of course, the Sun's light can be captured directly with solar panels. All of these green energies, wind, water, and solar, are just different and more immediate ways of harvesting the constant, clean, and colossal power of our nearest star. The Sun will, one day, be responsible for the end of life on Earth.
Long before it becomes a red giant, the Sun is
very, very slowly getting brighter. As it ages, its core slowly contracts, which heats it up and causes the fusion to burn just a little bit hotter. It is estimated that the Sun is getting about 10% brighter every billion years. This is a very slow change, but in about 1 billion years from now, this extra 10% of sunlight will be enough to trigger a runaway greenhouse effect on Earth. The oceans will begin to boil, turning our blue planet into a hot, steamy, and uninhabitable Venus. The habitable zone of our Sun will slowly move outward, and the Earth will be left behind. The solar maximum, the peak of the 11-year cycle, is a time of great beauty and danger. It is when the aurora is the most frequent and most spectacular. But it is also when solar flares and CMEs are most common. These solar storms can disrupt our satellites, which we rely on for GPS, for communications, and for weather forecasting. They can knock out power grids for days or even weeks. We are, as a species, becoming more and more reliant on technology, and at the same time, we are becoming more and more vulnerable to the whims, the weather of our very own active and turbulent star. 2. The Sun is in a quiet, suburban part of our Milky Way galaxy. We are in one of the galaxy's spiral arms, the Orion Cygnus arm. But we are not in a dense, crowded downtown region. We are in a relatively peaceful, sparse area. This is a very fortunate place to be. If we were closer to the galactic center or in a dense star-forming nebula, we would be much closer to other massive stars. We would be bathed in more intense radiation, and we would be at a much higher risk of a nearby supernova explosion, an event so powerful it could strip away our planet's atmosphere. Our quiet, galactic neighborhood is another key part of our planet's long, stable, and fortunate history. The granules on the Sun's surface are the visible caps of the convection cells. They are the same size as a large country, but they only live for about 10 minutes. They are born, they bubble to the surface, they release their heat, and then they are pushed aside and sink back down. This means the entire surface of the Sun, an area thousands of times larger than the Earth, is being resurfaced, overturned, and recycled every 10 minutes. It is a level of dynamic, constant, and roiling activity that is almost impossible to imagine. A vast, bubbling, and fiery ocean, constantly renewing itself. See, to the sun's corona, its million-degree atmosphere is so hot that it boils off particles at 1,000,000 miles an hour. But it is also, at the same time, incredibly thin. The plasma in the corona is a near-perfect vacuum, billions of times less dense than the air you are breathing. This is why it is so faint and why we can only see it when the sun's bright face is blocked. If you could stand in the corona, you would not feel hot. The particles there are moving at incredible speeds, which is the temperature, but there are so few of them that they would not be able to transfer that heat to you. You would, in fact, freeze in this million-degree, ghostly thin and ethereal atmosphere. 95. The sun's energy is what creates the jet streams on Earth, the high-speed rivers of air, high in our atmosphere, that circle the globe. These, again, are caused by the temperature difference between the hot equator and the cold poles. This heat imbalance is what drives our weather, and this motion, when combined with the fast spin of the Earth, Coriolis effect, causes these vast, flowing currents of air to form. These jet streams are what steer our storm systems, and they are what airplanes will often ride to travel faster. A high-altitude river of wind created by the sun and steered by the spin of our planet. Think of the sun's solar wind as it flows out and fills the heliosphere is a plasma, a gas of charged particles. This means it can carry the sun's magnetic field with it. The sun's magnetic field is frozen into this flowing plasma. So, as the solar wind flows past the Earth, it is a magnetized wind. It is this interplanetary magnetic field that connects to our Earth's magnetic field. If the sun's magnetic field in the solar wind is pointing south, it can open a door in our planet's defenses, allowing the solar wind to pour in, triggering the beautiful and powerful displays of the aurora. But the final black dwarf star that our sun will become is a theoretical object. The universe is only a 13.8 billion years old. A white dwarf, the hot, dense ember, is so well insulated and has so much stored heat that it takes trillions of years for it to radiate all of its heat away and go cold. This is a timescale hundreds of times longer than the current age of the universe. This means that no black dwarfs yet exist. Every white dwarf that has ever been created in the entire history of the cosmos is still a white dwarf, a hot, glowing ember still in the very, very early stages of its long, slow, and final cooling process. The sun is the anchor of our solar system, but it is not the center of our galaxy. Our sun and our entire solar system is in a vast 230 million year orbit around the center of the Milky Way. At the very center of our galaxy, 26,000 light-years away, is a supermassive black hole, an object of truly profound mass and gravity called Sagittarius A star. It is an object with the mass of 4 million suns crushed into a single invisible point. This is the true gravitational anchor of our entire galaxy. Our sun, which seems so powerful to us, is just one of hundreds of billions of stars, all in a vast, graceful, gravitational dance around this distant, dark and silent central object. Date. The interstellar medium, the thin fog between the stars that our sun is moving through, is not empty. It is filled with the ashes of long dead stars. It is a thin soup of hydrogen, helium, and the stardust, the carbon, oxygen, and iron that was scattered by ancient supernovas. This fog is the raw material for the next generation. In some places, this gas will grow cold and dense, and gravity will begin to pull it together. It will collapse, and in its center, new protostars will ignite, just as our sun did 4.6 billion years ago. The galaxy is a vast, self-sustaining ecosystem where the ashes of one generation of stars become the seeds for the next. Hundreds, and so we see our sun not as just a light in the sky, but as a star. It is a dynamic, active, and magnetic engine. It is our anchor holding our planet in a gentle, steady orbit. It is our furnace, its ancient light providing the warmth and the energy for all of life. It is our shield, its solar wind creating a protective bubble that shelters us from the galaxy. It is our past, as we are made from the stardust of its ancestors. And it is our future, as its slow, steady changes will one day, in the deep, distant future, determine the final fate of our world. It is our constant, our life source, and our own personal and profoundly beautiful connection to the rest of the vast and wondrous cosmos, while the sun's light, as it passes through our atmosphere, creates the blue of the sky, but it also creates the blue of the deep ocean. When sunlight strikes the water molecules are very good at absorbing the warmer colors of the spectrum, the reds, oranges, and yellows. But the blue light is not absorbed as easily. It is able to penetrate much deeper, and it is also scattered by the water molecules in much the same way the atmosphere scatters light. This means that as you go deeper, all other colors are filtered out, and the only light that remains, the only light that is scattered back to our eyes, is that deep, rich, and calming blue. The ocean is blue because it is reflecting the sky, but also because it is itself a vast, liquid filter for the sun's white light. 2. The sun's 11-year cycle of activity is a rhythm that, in a way, we can see recorded on Earth. When the sun is very active, at its solar maximum, its powerful solar wind and magnetic field do a better job of shielding our entire solar system from the interstellar cosmic rays that come from deep space. With this stronger shield, fewer of these cosmic rays get to Earth. When fewer cosmic rays strike our atmosphere, it leads to the creation of less of a special isotope, carbon-14. This carbon-14 is absorbed by all living things, including trees. This means that by measuring the amount of carbon-14 in the tree rings of ancient, fossilized trees, scientists can look back in time for thousands of years and see the faint, steady, 11-year heartbeat of the sun's cycle, recorded in the wood of our own planet. 3. The photosphere, the sun's 6,000-degree surface, is the coolest part of the sun's atmosphere. Just above it lies the chromosphere, or sphere of color, which is even hotter, reaching 20,000 degrees. And above that, the corona, the faint, ghostly halo, which mysteriously soars to millions of degrees. There is a very thin, very turbulent transition region that separates the chromosphere and the corona. In this incredibly narrow boundary, only a few thousand miles thick, the temperature makes a jump of almost 1,000,000 degrees. It is one of the most violent and energetic, yet invisible, layers of the sun, the mysterious, fiery boundary between the sun's warm surface and its superheated outer atmosphere. 4. The sun's energy is the engine that drives the growth of phytoplankton in the ocean. These are microscopic, single-celled plants that float in the sunlit surface layers of the sea. They are, in a way, the grass of the ocean. They perform photosynthesis, absorbing the sun's light and turning it into food. They are the very, very bottom of the entire oceanic food web, feeding everything from tiny zooplankton to the largest whales on Earth. But more than that, these tiny, sun-powered, microscopic plants are so numerous that they collectively produce more than half of all the oxygen that we breathe on this planet. Every other breath you take is a quiet, invisible gift from the sun captured by these tiny, drifting, ocean-going plants. 5. The sun, in its constant, 230 million year orbit around the center of our galaxy is not traveling in a flat, simple circle. It is also bobbing up and down. As it orbits, the galaxy's gravity pulls it, and it bobs gently up and down through the flat plane of the galactic disk in a slow, gentle, wave-like motion. It passes through the dense central plane of the galaxy about once every 30 million years or so. It is a slow cosmic undulation, a gentle, wave-like ride that our entire solar system is taking, as we and our star are carried in the vast, starry, and spinning river of the Milky Way. With the sun's solar wind, the constant 1 million mile per hour stream of particles is what creates the tails of comets. Comets are dirty snowballs, ancient frozen balls of ice, dust, and rock, left over from the formation of the solar system. For most of their lives, they are in the cold, dark outer solar system and are invisible. But as their orbit brings them in toward the sun's warmth begins to heat the snowball. The ice turns directly into gas, or sublimates, and this gas streams off the comet, carrying dust with it, to form a coma, a glowing, fuzzy atmosphere. Then, the sun's solar wind and the pressure of the sunlight itself pushes this gas and dust, blowing it away from the comet, to create the two beautiful long tails that we see, a gas tail and a dust tail, always and only pointing away from our star. So 7, our sun is a population I star. This is a generation of stars, and it means that our sun is a metal-rich star. In astronomy, metal means any element that is not hydrogen or helium. A population I star, like our sun, is a second generation or third generation star.
It means it was born from a cloud of gas that had already been seeded with the stardust, the carbon,
the iron, the oxygen from a previous generation of stars, the population II stars, which had lived, died, and exploded. The very fact that our sun contains these metals is the reason that rocky planets like Earth and life like us could form at all. We are here because our sun is not one of the original, firstborn stars of the universe. There is a sweet spot in our solar system, a habitable zone, sometimes called the Goldilocks zone. This is the narrow, ring-shaped region around our sun where the temperature is not too hot and not too cold, but just right for liquid water to exist on the surface of a planet. If the Earth were much closer to the sun, our oceans would boil away. If we were much further out, they would freeze into a solid, global sheet of ice. 109. The light from the sun is not just one thing. It is a vast spectrum of energy. It produces the visible light that we can see, which is just a tiny, tiny slice of its full output. It also produces infrared light, which we cannot see, but which we feel on our skin as heat. It produces the ultraviolet, or UV light, which is invisible but powerful enough to cause a sunburn. And in its most violent moments, in a solar flare, it produces X-rays and gamma rays, the most high-energy, penetrating forms of light in the universe. Our star is shining in all of these colors at once, a full, broad-spectrum electromagnetic orchestra, though our eyes are only built to see a few quiet notes. 10. The sun's solar wind is not a wind of air, but a plasma, a gas where the electrons have been stripped from their atoms, leaving a soup of charged particles. This means the solar wind is an excellent conductor of electricity. As it flows out from the sun, it drags the sun's magnetic field with it. The sun's rotation, which is faster at the equator, twists this magnetic field, and the solar wind carries this twist out into space. This creates a vast, spinning, spiral-shaped pinwheel of magnetism all across the solar system. This is the interplanetary magnetic field, a Parker spiral. And as the Earth orbits, it is constantly flying through these vast, sweeping, spiral spokes of the Sun's magnetic field. But dear son, the twisting of the Sun's magnetic field from its fast equator and slow poles is what stretches and powers the magnetic field lines. It is like twisting an elastic band. You are storing energy in it. This stretching and tangling is what builds up the tension over the 11-year solar cycle. A sunspot is a place where one of these kinks, one of these tangled ropes of magnetism, has become so powerful that it has floated to the surface like a buoy of magnetism. The solar flare is the snap, the moment when that over-twisted elastic band, that tangled rope of magnetism, finally breaks and releases all of its stored energy in a single, sudden, violent flash. The Sun, as it orbits the center of the galaxy, is one of about 200 to 400 billion other stars in our Milky Way. It is a vast, spiral galaxy, a spinning pinwheel of stars, gas, and dust. Our Sun is located in one of the quieter spiral arms, about 2/3 of the way out from the dense, chaotic, and energetic downtown center. We are in a calm, suburban neighborhood. This is a very fortunate place for a planet with life. We are far enough from the center to be safe from the intense radiation and from the supermassive black hole that lurks there. And we are not in a dense star cluster, where a nearby exploding star, a supernova, would be a constant and deadly threat. The Sun, for all its power, is a dwarf star. Its official spectral classification is a G2V or G2V star. This is sometimes, and somewhat confusingly, called a yellow dwarf. It is not a giant star. It is not a supergiant. It is a dwarf star, which simply means it is on the main sequence, the long, stable, adult phase of its life, where it is calmly burning or fusing hydrogen in its core. This dwarf status is a sign of its stability. It is not in a chaotic, giant phase. It is in the prime of its life, a long, quiet, 10 billion year long adulthood, and we are lucky enough to be living in the middle of that long, peaceful, and dwarf phase. The Sun's light is what gives color to our world. An object like a red apple is not making red light. It is a filter for sunlight. When the Sun's white light, which contains all colors, hits the apple, the skin of the apple has a chemical, a pigment, that absorbs all of the blue light and the green light and the yellow light. The only color it does not absorb, the only color it reflects back to our eyes is red. The apple is red because it is rejecting the red part of the Sun's light. A white piece of paper is reflecting all the colors, and a black object is absorbing all the colors. Every color we see is just a different, beautiful and subtractive dance with the Sun's white light. The Sun's energy is what, in a very real way, lifts the water up into the sky. A single, large, fluffy cumulus cloud, a fair weather cloud, can weigh as much as 100 elephants. It is floating because it is not a thing, but a process. It is a cloud of tiny, microscopic water droplets, so small and light that the updrafts of warm, rising air, which is also heated by the Sun, can easily hold them aloft. A cloud is the visible tip of a vast, invisible column of rising, sun-heated, moist air. It is a river in the sky, a river of water that was lifted there, molecule by molecule, by the pure, silent, and steady energy of our star. Sixth, in the Sun's chromosphere, the sphere of color, is a forest of spicules. These are giant, fiery jets of plasma as wide as a city that are constantly shooting up from the surface. They are born in a few seconds, jet upward at 50,000 miles per hour to a height of thousands of miles, and then, in a matter of 10 or 15 minutes, they collapse and fade away. At any given moment, the entire surface of the sun is covered in millions of these spicules. It is not a calm layer. It is a dynamic, hairy and bristly layer, a forest of fire constantly in motion, a transition between the bubbling surface below and the ethereal corona above. Can the solar wind, the sun's constant, million-mile-per-hour breath, is not just a wind. It is a plasma that carries the sun's magnetic field. This interplanetary magnetic field is what shields us. Our solar system is flying through the interstellar medium, which is filled with interstellar cosmic rays from distant, exploded stars. Our sun's heliosphere, this bubble of wind and magnetism, is a force field. It pushes back against these interstellar rays, deflecting about 70% of them and shielding the inner planets, including Earth, from this harsher galactic radiation. We are living inside a protective magnetic cocoon that is being inflated constantly by our star. 18. The Oort cloud, the final gravitational boundary of our solar system, is a vast theoretical shell of icy bodies, a light year from the sun. It is a cold, dark, and silent reservoir of comets. It is leftover material from the birth of the solar system, flung out to this immense distance by the gravity of the giant planets like Jupiter and Saturn in the solar system's youth. These comets are in a deep freeze, barely held by the sun's faint, distant gravity. But sometimes the gravity of a passing star or the tide of the galaxy itself will give one of them a tiny nudge, and it will fall in a journey that takes millions of years in toward the sun to become a new, long-period comet, a visitor from the cold, dark, and silent edge of our sun's kingdom. Paint the sun as we see it is a G2V star, a yellow dwarf. But this color is just a label for its surface temperature. A star's color is the peak of its light output. A cool star, like a red dwarf, peaks in the red and infrared part of the spectrum. A hot star, a blue giant, peaks in the blue and ultraviolet. Our sun, at 6,000 degrees, has a peak in the green-yellow part of the spectrum. Our eyes, however, see all of its light mixed together, and our atmosphere scatters the blue, so we perceive it as yellow. But its true color, its peak output, is green, a peak that our own eyes have evolved to be most sensitive to, a beautiful evolutionary tuning to the color of our home star. 20. The Sun, in about 5 billion years, will become a red giant. It will swell up, and it will swallow Mercury and Venus and possibly the Earth. But even if the Earth is not swallowed, it will be sterilized. The red giant sun will be so large and so luminous that the habitable zone, the Goldilocks zone of liquid water, will move. It will move outward to the outer solar system. For a brief period, a few 100 million years, the habitable zone will be at the orbit of Jupiter and Saturn. It is possible that, for a short time, the ice on their moons, like Europa or Enceladus, will melt, and these tiny ice worlds will briefly become ocean worlds. A final, habitable epilogue for our solar system, warmed by the dying giant sun. The sunspots, The cool, dark, planet-sized patches on the sun's surface
are islands of intense magnetism.
They are dark because the magnetic field is so strong that it chokes off the convection from below. It stops the hot bubbles of gas from rising to the surface. It is like putting a magnetic lid on a boiling pot. Because the heat from below is blocked, that patch of the surface cools down from 6,000 degrees to 4,000 degrees. It is not dark, it is just dimmer than the blindingly bright ocean of fire around it. A sunspot is a shadow cast by an invisible rope of magnetism. And so our quiet, golden journey toward the sun draws to a close. We have drifted through its colossal, fiery heart, and we have floated on its million-mile-per-hour solar wind. We have seen how its ancient light, after a journey of 100,000 years, finally breaks free to give us our blue sky, our green leaves, and our very lives. We have felt its gentle, constant gravity, the anchor that holds our small, blue world in a perfect, life-giving orbit.
A steady hand that has guided us for all of time. This star, our sun,
is not out there. It is in here. The light it creates is the energy that powers every muscle and every thought. The stardust in its body is the stardust in our own. The iron in your blood, the calcium in your bones, all of it was forged in a star, just like our sun. You are a child of the cosmos, made from the same ancient fiery material as the star that warms you. You are as much a part of the universe as the sun itself, a tiny, wondrous piece of it that has become aware. But those vast, warm, and golden thoughts can now be allowed to fade. The journey is done. All that wonder can now dissolve into a simple, gentle, and comfortable warmth. There is nothing left for you to do.
Nothing to think about. Your only task now is to let go.
To feel the comfort of where you are, to feel the weight of your body, heavy, supported, and at peace. You can let go of the day, and you can let go of my voice. Allow yourself to drift on that last, gentle, warming ray of light. Let it guide you into a deep, calm, and restorative sleep. You are safe. All is well. May your dreams be peaceful. Good night.